Okay, let's start. Welcome to the spring semester. This is Math 3210, first section, Foundations of Analysis 1. This is the first of a series of classes. My name is Alp. Email is my last name, Usman, at math.utah.edu. I'm glad I came prepared. Okay. Yeah, I'm a postdoc here at the University of Utah at the math department, really, which is, I guess, that side. So today is going to be syllabus day. Probably we're not going to talk about anything in terms of math, but still. Yeah, I didn't write. Okay, so the syllabus is on Canvas. I'm not going to hand out, physical printouts. On syllabus, I didn't write anything about the office hours. I just said by appointment. Based on my experience, that works sort of the best, because otherwise, especially at a university like this, it's hard to find a time that works for most people or for all people typically, and then people tend to not come to office hours and stuff like that. So I'd rather have you take the initiative to set up appointments with me using email and all that. Okay, so this is a proof-based class. And the emphasis will be on developing mathematical maturity. So how many of you have heard this phrase, mathematical maturity? Any guesses as to what that should mean?
Moving from like grade school, just calculating, to like professional, like proof making.
Sure. Yeah. Any other?
Maybe just like a deeper understanding of why it works the way it works.
Yeah, I would say so too. I mean, the way I think about it is that, okay, so yes, proof making is an important part of doing math, especially pure math, but a lot of you are not going to be mathematicians as far as I'm concerned, based on your majors. You might well be, but that's not the expectation of this class. As far as I'm concerned, mathematical maturity is basically about the following. You see a sort of high-level math thing that is definitely beyond your pay grade, and instead of freaking out because you don't understand the symbols, you might still freak out, but at the very least, you should have being able to develop some sort of like method to tackle it. This complicated thing that you encounter, that's sort of like mathematical maturity. I should also mention that most of the documents that I'm going to put on Canvas, they have hyperlinks, and the Canvas system doesn't really do well with hyperlinks. But if you were to download the PDF files, you can just click on them. And so if you were to click on mathematical maturity, it's going to take you to a blog post by Terence Tao, one of the greatest mathematicians of our time, perhaps of all time, of all times. And one of the things he says is that there's this pre-rigorous era. This is sort of like the type of math that you do in the standard calculus classes. They justify that this should be that way or that should be that way based on intuition. Obviously, this is true and stuff. And then you take a class like this, and that's really about understanding the formalism and being able to be rigorous a little bit. But then you don't stop there, really. You go beyond, and that is what is called the post-rigorous level. Because on the one hand, yes, it is good to be able to prove things. It's also important to be able to approach things from an intuitive point of view. So in this class, we're going to learn how to prove things, but we also will try to switch over to this post-rigorous stage a little bit. In particular, on rigorous argumentation rather than calculation of the values of certain limits, integrals, or derivatives. I might still ask you to compute things, of course, but Because there are certain complicated things that you can't compute unless you understand what is going on. Okay, we'll start with elementary logic and set theory, discuss main methods of documentation that are up to the modern standards of mathematical rigor, and then discuss differential and integral calculus of single variable, real valued functions. As adjacent topics, we'll study the convergence and divergence of sequences and series of numbers and functions. Expectations. As a student, you are expected to attend all lectures, which is 4 times a week, complete 12 problem sets, take 2 in-class midterm exams, and take a final exam. According to the university regulations, you should expect a workload of approximately 8 to 12 hours per week outside of lecture hours. So that's a lot of math time. You will have some familiarity with many ideas and notions we'll discuss throughout the semester. However, the focus on rigor can be hard to get accustomed to, especially if you're not familiar with these things. And it is likely that if you're taking this class, you're not that familiar. There's a certain culture shock associated switching from sort of calculate this to prove this. And there's going to be times when you see things, statements, they're obviously true to you, but then I'm going to ask you to prove it. And then you're going to realize that, oh, maybe proving it is not as straightforward. Maybe it is, but missing lectures or assignments can make it challenging to catch up. Please stay engaged and reach out if you encounter any disruptions. We're here to help, but your hard work and dedication will be essential to getting back on track. Learning objectives. Among the objectives in Math 3210 are that you learn how to use logical quantifiers, describe statements and the operations of and, or, and not in terms of sets, identify injective, surjective, and bijective relations and functions, parse mathematical proofs, distinguish levels of rigor in mathematical prose, write proofs in accordance with modern standards of mathematical rigor, which is basically the standards that were established, let's say, early in the 20th century. Now with the advent of AI and other proof checker systems and other things, now what a valid proof is sort of like going through some revision, but for our purposes, that's not going to be sort of within our horizon. Or maybe it'll be in our horizon, but we're not going to do something on lean or something like that. Approach numbers from a bottom-up point of view and make use of the completeness axiom and the Archimedean property. Use the notions of supremum and infimum. You see, this is where sort of things start to get a little complicated. So we have max and min, of course, but then there are these associated or similar concepts, supremum instead of maximum, and infimum instead of minimum. They are sort of like pretty much the same, but not quite. And somehow supremum and infimum are terms that are more mathematically robust. And we're going to have to learn what they mean and learn how to use them. Derive the consequences of the triangular inequality for numbers and functions. Use sequences and series of numbers and functions. Identify when a sequence or series converges and in which sense. So typically in a calculus, in a standard calculus course, you're given a series or whatever, and they ask you what is the sum. Now we're going to encounter a lot of series in this class that are going to be possibly hard to evaluate, but still, instead of finding the limit, you can ask for something less, which is that whether or not it converges. Okay, and probably you've seen some tests that tell you, oh, this series converges and not, and we're going to look into that as well. Use the notions of accumulation points, limit inferior and limit superior of a sequence of numbers. This limit inferior and limit superior are related to these weird notions, supremum and infimum, that we're going to study before. Prove and use the fundamental theorems governing continuous functions, including the maximum principle and intermediate value theorem. How many of you remember the intermediate value theorem? Couple. Okay. Which basically says, just to remind ourselves, It's nothing crazy, okay? So if you have a continuous function, okay, that's a continuous function. Why is it continuous? Because I was able to draw its graph without taking the marker off the board, right? Like there are no discontinuities. Intermediate value theorem says that your function takes any value in between. Okay. Obviously, that should be true. We're going to see why. We're going to prove it rigorously. Distinguish continuous functions from uniformly continuous functions. So that's a different type of continuity that, in fact, humanity had to deal with for a while before all this stuff was polished and understood properly. Prove and use the fundamental theorems governing differentiable functions, including the chain rule, inverse function theorem, mean value and role theorems, and L'Hopital rule. Probably most of these are familiar to at least somewhat, you might remember them from your earlier classes. Define the notion of Riemann integrability. Now, as far as I'm concerned, when it comes to integration, we're going to have the most divergence from what you learned before. Because somehow defining the Riemann integral, if you try to do it properly, it's not as straightforward as defining derivatives straightforwardly. And in the schedule too, you're going to see that we're going to have like 4 weeks for integration. And of course, prove and use the fundamental theorem of calculus. This is the main, probably, topic of this class. Prove and use the fundamental theorems governing Riemann integrable functions, including the change of variables formula, so the U substitution, right, and integration by parts. Define elementary functions like exponential and logarithm, and prove and use Taylor approximation. Okay, I'm not going to go through the schedule. You can read it on your own. So I like to be as specific as possible when it comes to the schedule, but it's tentative, of course, and there are always like things that ends up needing to be changed and all that stuff. So we'll see. I'm going to try to stick as much as possible to the schedule, but we'll see. And like I said, maybe I should comment on it a little bit. So the foundations part is basically maybe 2 to 3 weeks. So it is de-emphasized compared to other sort of reincarnations of this class. There are many instructors who taught this class over the years, and as I was designing this syllabus, I sort of looked at pretty much all of them, and I sort of like changed it a little bit so that it makes more sense for me at least. We're going to spend 2 weeks on continuity, and 2 weeks on differential calculus, and 4 weeks on integral calculus. It's not exactly 4, it's 3.5, but still. And then we're going to have 3 weeks on series. You see the more messy parts, we're going to spend more time. Okay. Grades. So, maybe I should write it. So 5% attendance. I'm going to take attendance at random classes. %. Problem sets, we're going to have 12 of them. They're going to contribute 30%, sorry, to the final grade. And our TA this semester is a strong TA as well, so I'm happy about that. It's going to be good, I hope. Midterm 1. 20%. Midterm 2, again, 20%. And then final, 25. Okay. A starts at 90%, and then you drop 5% for each letter degradation. So A minus is 85 and so on. Okay. Textbook that we're going to use typically is the main textbook, the university, or the one that the department suggests. Joe Taylor's Foundations of Analysis. Joe Taylor was faculty here for a long time, I think. So it's the in-house textbook. And in class, I'm going to try to stick as much as possible to the textbook. I might change things a little bit, but still. And as supplements, I would suggest looking at Terence Tao's lecture notes and lecture notes by this Turkish mathematician. Oh, by the way, I'm Turkish as well. This Turkish mathematician, Ali Ülger. And it's kind of a weird thing, but I thought it would be nice to share with you the source that I learned this stuff from. And presumably, I mean, I learned this stuff maybe 10 years ago or something, but over time, the way you learn things for the first time sort of seeps into everything. So it might be instructive to have a look at these notes as well. Okay, any questions so far? Yes?
Can you spell the name of the Turkish mathematician?
It's on the syllabus. Yes. Any other questions? Yes.
Are any of the problem sets dropped at the end of the semester?
Possibly, yes. Yeah, I mean, depending on the performance. Yeah. I typically drop 2 to 3 of them, but yeah. Any other questions?
What can we expect the problem sets to look like?
Okay, the problem sets are going to be like this. I'm going to be preparing them myself. But what I'm going to do is this. I use ChatGPT to scrape all the exercises from the book. Okay? And then I change them a little bit. And then there are a couple other books that I like. I look at them and stuff like that. So, I mean, there are other classes that I taught online. And you can have a look at them and see. Yeah, I like to. I spend a lot of time preparing the problem sets and the class is sort of like, I try to coordinate the class very, let's say, strongly relative to the problem sets and vice versa, and likewise the midterm exams. So the midterm exams typically are going to be mostly from the problem sets. But there might be 1 or 2 questions that are sort of no. It's going to be like that. Yeah, over time you'll have a sense, I hope. Any other questions? Okay, lectures. Attendance at all lectures is expected. Attendance at random lectures will be taken and will have an effect on the final grades. This is 5%. I mean, I just want you to come to all classes, basically, and of course, if you're sick and stuff like that, you should just let me know ahead of time. The number of lectures when attendance will be taken will also be random. A certain number of recorded attendance days may be dropped at the end of the semester. On weekends, when a midterm is scheduled, so the weeks 5 and 11, first 2 classes will focus on topics as usual, whereas the class before the midterm is reserved for review. Likewise, the 2 classes on the last week, which is week 15, will be reserved for review. And I'm recording the lectures, as you see, and there's a YouTube playlist, and at the end of each week, I'm going to sort of edit them together, and there's going to be 1 video per week. And I think, based on experience, I've been doing this for a while now, and based on experience, it is very helpful to students and for myself as well. I sort of forget what I talked about in class, and I can just look at the lectures and all that stuff. And another thing I do is I annotate the video so that you have sort of, this is an example, this is a theorem, this is the proof of the theorem, and so on. So I hope you'll make use of this. Problem sets. 12 problem sets will be assigned throughout the semester, typically on a weekly basis, excluding weeks with midterms. So basically, we're going to have 1 problem set due every Friday, except the Fridays when we have a midterm. Okay? And then there's also a problem set due the day the finals is scheduled, which is another Friday. So at any given time, you're only going to have 1 thing to worry about. Either your preparing for a midterm or you're trying to complete a problem set. Late submissions up to 24 hours after the deadline will be accepted with a 10% penalty. Submissions more than 24 hours late will not be accepted unless you contact the course staff with a valid excuse before the 24-hour extension expires. A certain number of problem sets with lowest scores may be dropped at the end of the semester. Grading criteria. The problem sets will be graded partly on completion and partly on accuracy, validity, and presentation documentation. So typically this means the following. Typically we're going to have, let's say, 5 or 6 problems. And I'm not going to tell you which one I will be grading specifically. And when I grade a problem set, a problem from a problem set, that's going to be for completion. And the rest typically is going to be graded by RTA. So you're not going to know which problem from a problem set is going to be graded for accuracy. But so hopefully that'll sort of push you to write your answers, properly for all problems. Submission details. For each problem set, you are required to submit a form through Google Forms and digital copies of your work through Gradescope. Detailed submission instructions will be provided in each problem set specification. So this business about the Google Forms, it has 2 functions. One function is that I ask how you're doing and stuff. So I'm going to ask things like, okay, how long did it take you to finish this problem set? And I'm going to aggregate all that data, and based on that, we're going to sort of make adjustments. Maybe I'm sort of like asking too hard questions, or maybe it's too easy and stuff like that. And the second of all is that I'm going to ask things like, oh, I did this problem set by myself and I didn't use this or that thing. I mean, of course you can lie, but you're not supposed to lie. Conflicting instructions and deadlines. The submission deadlines and methods detailed in the problem set specifications, i.e. the problem PDF files embedded in the associated assignment web pages on Canvas. Canvas and Gradescope may differ. Always adhere to the deadline and instructions in the specification document, as these will be the accurate guidelines. So right now, on Canvas, if you look, there are assignments already there, but they're all empty. As time goes by, I'm going to populate them. Okay. So for instance, problem set 1 is going to be due not this Friday, but next Friday, and I'm going to release it by this Friday. Okay. So you're going to have basically a week to start and finish a problem set. Midterm exams. 2 midterm exams. First one is on the Friday of week 5, which is February 7 in class, covering topics from week 1 to 5. Second midterm on March 28, Friday of week 11, covering topics from 6 to 11, and then there's going to be a final exam. During the midterm exams, the use of external resources, including colleagues, books, and electronics, will not be permitted. Your exams will be digitized and uploaded to Gradescope by the staff, by me, and you will have access to view how your exams were graded. And likewise, the final exam is scheduled to be on April 25th from 8 to 10, again here, and the final exam will be cumulative. Again, it's going to be closed books. You cannot use anything except pen and all that stuff. Okay. Any questions so far? Okay. Math Center, especially for this class, I think Math Center is pretty good. There's a bunch of good people there that I know. In addition to the office hours held by the course staff, the Math Center is an excellent resource for assistance with your studies, located in the basement connecting the 2 math buildings. So we have 2 math buildings here, over there. JWB, which is where my office is at, and LCB, and there's like a tunnel, okay, that connects the 2. And there's like, that's where you find the Math Center. The Math Center offers free drop-in as well as online support. Accessibility. The University of Utah seeks to provide equal access to its programs services and activities for people with disabilities. If you will need accommodations in this class, reasonable prior notice needs to be given to the CDA. CDA will work with you and the staff to make arrangements for accommodations. All written information in this course can be made available in an alternative format with prior notification to the Center for Disability and Access. Inclusivity and safety. Title IX makes it clear that violence and harassment based on sex and gender, which includes sexual orientation and gender identity expression, is a civil rights offense subject to the same kinds of accountability and the same kinds of support applied to offenses against other protected categories such as race, national origin, color, religion, age, status as a person with a disability, veteran status, or genetic information. If you or someone you know has been harassed or assaulted, you are encouraged to report it to the Title IX coordinator or the Office of the Dean of Students. And there's phone numbers and stuff here if you're in that situation. For support and confidential consultation, contact the Center for Student Wellness, SSB 328. Maybe they're moving actually. Never mind. To report to the police, contact the Department of Public Safety and just call the cops. And there are further safety resources under SafeU. And finally, academic honesty. You are expected to adhere to University of Utah policies regarding academic honesty. This means that ultimately all work you submit must be your own, created without unauthorized assistance, and all external resources, including generative tools, so this ChatGPT type stuff, and computer algebra systems must be properly cited and documented within your submissions. And you're going to do this using the Google form that I was mentioning. Any student who engages in academic dishonesty or who violates the professional and ethical standards may be subject to academic sanctions as per the University of Utah's student code. Generative AI and computer algebra systems. In this course, you may use generative tools like ChatGPT as well as computer algebra systems such as MATLAB. And probably MATLAB is not going to be too much help, but still might be useful, under specific guidelines. These tools are permitted to guide your understanding of problem sets and topics. When using them, you must submit logs of your interactions as part of your problem set submissions. So for instance, if you're using ChatGPT, there's a function there that allows you to share your conversation. These tools can also be used to verify calculations, but remember, computations are generally expected to be done manually unless explicitly stated otherwise. So ultimately, in this class, you should expect to learn the type of math that you should be able to do if there was like a, civilization collapse. We don't have any electricity or whatever, or you're stranded in an island, and for some reason you want to do math, and that's the type of math we're going to learn. You are responsible for ensuring the validity, accuracy, and relevance of your submissions, whether or not you use these tools. While encouraged, the use of such technology is not required for success in this class, which means that if you were to take this class, in the 1800s, it's pretty much all the same. There might be some, new things, but still. The policy governing the use of such technology is specific to Math 3210-001, this section. Other courses and sections may have different policies. And we have a regret clause. It says the following: if you commit an unreasonable act, but bring it to the staff's attention within 48 hours of the relevant submission, sanctions may be limited to that submission only, rather than leading to further disciplinary action. This clause will not be applied in the case of repeated violations. So let's say that you're, sleep deprived and stuff like that, and you're trying to finish the problem set, and you made the mistake of leaving it to the last minute, let's say, or last day, perhaps. And you have a lapse of judgment, and you sort of search online, and there's, Stack Exchange, and someone wrote the answer already, and you just copied and pasted it, and didn't say anything. After you sort of sleep a little bit and all that stuff, if you let me know within 48 hours, no harm done. That's what I'm saying there. Okay, and that's about it. Any questions about anything? Okay. So we have time until 10:30. So we have about 20 more minutes. Nice. So let's start. Let's start from the beginning. So the title of week 1 I called to be functions, and really this week we're going to study sort of more abstract stuff a little bit, sets, logic stuff, what is a function, what is a relation, and so on. And then starting from week 2, we're really going to switch over to the reals, the real line, which is sort of like the main ambient space for single variable calculus, right? So foundations of analysis 1 really is, we should think of it as advanced calculus, advanced single variable calculus. So okay. So I don't want to spend too much time on, logic and sets and all that stuff. I'm just going to introduce some notation today and, throughout this week. And then hopefully you'll get accustomed to these things as the semester progresses. Because the main point of this class is not, understanding, logic itself, or for instance, the construction of the reals. It's like a topic that the book spends quite a bit of time. But really to sort of connect formalism and calculus. And so let me just start with this. Logical symbols. Now, these are not necessary, strictly speaking, but certainly it helps quite a bit to compress information and expression. And in this class, typically what happens is that you end up needing to write the same thing over and over again. So it's going to sort of make it quite simpler, a lot simpler. And so there is a couple things. One of them is what is called for all, or for any. Okay. And then there is something called exists, or there exists. And then there's, maybe we might use this, there exists a unique. Okay, these three terms we're going to use quite often in this class. Well, for this, I'm going to use sort of upside down A. Okay. For exists, I'm going to use backwards E. See, E, A, and then when you have it, there exists unique, you just use backwards E with an, what do you call it? Exclamation. You're surprised somehow that there's a unique one. Okay. I'm just going to leave it at this. Instead of sort of looking into sort of random statements, I'd rather sort of move forward and then start using these terms, these symbols in the context of calculus. Okay, and of course we have other things. These have notations as well, but I'm not going to write them down. We have what is called and, or, there's XOR, which is, well, I'll mention it later. What else? Not. And then there's implication or implies. So using these, we're going to connect a bunch of statements and so on. And we're going to have in our theorems a bunch of like clauses. We're going to have if this and this and this, then this and that and that. We're going to have statements like this. Okay, that's all we need for now. Sets. Well, a set is just a bunch of things. Now, even though in this class we're really looking into rigorous things, we're not going to go all the way, into set theory and stuff like that. We're just going to still leave it as, as at the naive level, and, because I'd rather spend more time on calculus stuff. So a set is a bunch of things. Is a collection. A set is an aggregate of things. So one of the important sets that we're going to use, of course, is the set of real numbers. So example. In fact, let's write a bunch of number systems. So we have natural numbers. And so you write n for natural, and then you put a dash. That is what is called blackboard bold. And really, I'm not going to use this notation. I'm going to use some other notation that I'm going to write in a second. There is z with a dash. That's the integers. So the naturals start at 1, I think. 1, 2, 3, 4, 5, and so on. Integers, you have 0, 1, 2, 3, 4, 5, and also minus 1, minus 2, minus 3, and so on. So instead of n, because some people use n to denote integers starting at 0, some other people start at 1, and so on, I'm just going to write instead z sub greater than or equal to 1. Okay, it is more explicit. You don't need to guess. Is 0 included? Is it not included? And whenever people start, there's this thing. It's like some people say, oh, is 0 natural number? It's like you can just avoid it. Just say integer. I'm starting at 1, whatever. Q, rationals. So this is the ratio of two integers. And then the next thing that we're going to spend the most time with is the reals. Let me write the names of these. Naturals, natural numbers, integers, rational numbers, and then real numbers. Now, how do you describe these sets? I just wrote some symbols on the board and named them, and put like, how do you do math with them? There's a couple of different ways of writing down a set. So for instance, to write down the first set over there, set of natural numbers, one thing you can do is you can just list them down. And of course, there are infinitely many natural numbers, so how do you list them down? You just put ellipses. And you just say, okay, this is what I mean. So you can write it like this. You open curly braces, and then you're going to close it. 1, 2, 3, 4, dot, dot, dot. Okay? Now, if you're a very formalist person, you would say, oh, you know, this is a set with 5 elements, and you have 4 elements here, and this is the 5th element. But when we write it like this, we mean just the infinitely many integers that we have over there. Okay? We're not going to be that strict about these kind of things. Okay. Integers. Well, I can write it like this. 0, plus minus 1, plus minus 2, plus minus 3, and so on. Again, if you're more, you know, formally inclined, you would want to write it like plus 1 and then minus 1 with a comma and so on, but it's clear what I mean here. Okay, and in this class, even though we're trying to understand proofs and stuff like that and learn how to write proofs, I don't want to be a stickler about, you know, being very formal. Now, one thing I should mention here is that when you're writing these curly braces, the order in which you write things doesn't matter. So this is an unordered list, if you want. Okay? So I could have just as well written instead this, oh, maybe I want to write 1, 3, 5, and then it goes on, and then 2, 4, 6, and then it goes on. Okay? They're the same thing. Okay? Next one, Q. So the set of rationals. Now at this point, here's a different way of writing down a set. You can do this. You pretty much always open curly braces and then close curly braces. But instead of listing the elements, what you can do is you can use what is called the set builder notation, which says the following. Start with open braces, close braces, put a bar, or maybe semicolon, or colon, I guess. I like to use bar. To the left of the bar, you put the form of a typical element in that set that you want. In this case, I want to say something like this, P over Q. A typical element in the set of rationals is going to be a ratio, right? To the right of the bar, you put the conditions. P and Q, I need to say something about them. Well, P and Q are integers. P and Q, integers. Okay? Any issues with this?
We allow Q to be 0.
Right? You want to say something about Q not being 0. Why? Because you don't divide by 0 and all that stuff. I mean, there are other number systems where you allow division by 0, but let's leave it at that. Now, describing R, is going to be not that straightforward. We're going to have to discuss how to go from Q to R. What it is that somehow, if you were to think of all the rational numbers, and if you were to line them up, because given any two rational numbers, you can say, oh, this one is smaller than the other one, which means that you can think of them as part of a continuum. Well, it turns out that if you were to think of this continuum, if you were to just stick to rational numbers, there's a bunch of gaps. Because it turns out that there's a bunch of numbers that are not rational, but still real. So for now, we'll just leave it as is. No, I'm not going to say later. And this was a problem that humanity came across a long time ago, right? Because they were into geometry and stuff. And they looked at this right triangle with two sides of equal length, let's say 1. And then, of course, I'm sure a lot of you know that this length should be root 2. And then they said, oh, how can I write root 2 as P over Q? Okay, and then they realized that you cannot do it. You cannot write root 2 as a ratio of two integers. Okay, and then over time, people realize, oh, maybe this rationals is kind of buggy. Well, at least to do some geometry and stuff like that, certainly. But when it comes to computers, for instance, it turns out that real numbers is perhaps a little bit obsolete because there's no such thing as infinite resolution, right? Infinitely many digits after the dot when you're trying to write down a number, at least for the purposes of computation. There's always a certain cutoff and stuff like that, and you don't really use it. And then people realize that even beyond reals, there are more important things or more useful things depending on the context, like the complex numbers or the quaternions and stuff like that, which we're not going to get to. Okay. So maybe I should leave it as an exercise to try to come up with an argument, let's say. For the statement that root 2 is not a rational number. For next time, let's think about that. Let me write it down. Exercise. Now we're going to discuss later this week what are sort of valid methods of proof. But let me just say for now, one thing you can use is what is called proof by contradiction. Which means that you say, okay, say it is a rational number. And here's a new symbol. This means element, right? Like I'm saying, say root 2 is an element in the rationals. I'm going to mention this tomorrow as well. But so there are, you see, there are P and Q integers, Q not equal to 0, such that root 2 equals P over Q. Your aim here is to keep pushing this idea, this argumentation, to get something bizarre. Get a bizarre thing, get a wrong thing, get an obviously wrong thing. Okay, that's it for today. Thank you. I'll see you tomorrow. Okay, let's start. Good morning. So yesterday we stopped at this exercise that I gave you, which was to prove that this number, root 2, which Pythagoreans, ancient Greek people, were certain existed, I guess, is not a rational number. That is to say, it cannot be written as the ratio of two integers. And I thought about it a little bit, and I want to leave it to you still, perhaps until tomorrow or Friday, where we start talking about proof methods, more specific, and I think I want to do it in class as well, because I think it's a very instructive proof, and it's one of the classical proofs that you sort of do when you start thinking about how to prove things. So we're going to continue today on the foundations and stuff. I wanted to mention one thing, which is this Wason selection task, or it's also called the 4-card problem. It's something about logic, but it's also part of like psychology, and it was about like how people argue or think about certain logical statements and stuff. And then once we talk about this a little bit, I want to say a couple of words about how to approach statements in this class. So first of all, how many of you have heard of this? It's a psychology experiment. So the experiment is the following. You're told that there's a deck of cards. These are supposed to be cards, such that on one side for each card is a number, is an integer. On one side, and a color, that is to say either blue or red, on the other side, on the back side. Okay, this you're given. And now, somehow, they give you 4 cards. And you see the following. One of them is 3. The other one is 8. The next one, you see blue. So blue. And then the final one is red. Okay? This is the setup. Now the question is the following. You're given the following logical statements. If a card has an even number on one side, on the opposite side, it must be blue. If, then, its opposite side must be blue. Now, they don't tell you if this is correct or not. Okay, and that's the task. Your task is to do this. Your task is to flip as few cards as possible to verify or deny that this statement is true. Okay. Any questions about this? So the point is, like, you want to sort of like test the situation, right? Like maybe you want to flip this and stuff. But this is all you care about, nothing else. The question is, which cards must you be flipping to verify or deny?
The 8 and the blue.
8 and the blue. Any other guesses?
You would have to flip the red one as well, because if it's on the other side.
Okay. Any other? You don't have to flip the blue. Okay. Okay, so there's an intersection there that is, I think, correct. But let's go step by step. Do I need to flip 3? I don't need to flip 3 because the hypothesis is that if a card has an even number on one side, so I don't need to do anything about this. I could, of course, but that's redundant. So let me just write it here. Have to flip. Okay, not 3. How about 8? Well, 8 obviously is an even number because, a number being even means it's divisible by 2, and if you divide this by 2, you get 4. It is divisible. And so it has 8, so I need to flip it to verify. So I need to see. Maybe it is blue, maybe it is red. I have to flip 8. like you were suggesting. Now blue. This is where things get complicated a little bit. And this is what is called, what we're going to call contrapositive. So this statement is of the form P, a card having an even number on one side, let me not write it, implies some other statement Q, which means a card, so Q stands for a card has blue on the other side. Turns out that this is equivalent, logically equivalent, and this is sort of the notation that I use. Not Q implies not P. So this is what we're going to call contrapositive. Which will be one of the main methods of proof that we're going to use. Now, the reason why I don't need to flip this is that this statement doesn't say anything about what happens if on one side you have an odd number. Maybe it is also the case that for some cards, for some odd numbers, on the other side you have blue. I don't care. But this, you see, this is this case. Q was, on one side it is blue, not Q here, then stands for, on one side it is red. This means that this statement is equivalent to saying that if a card is blue, if a card is red on one side, on the opposite side it must be odd. Okay? So I need to flip red as well. Does this make sense? Okay. Now, some of you are into econ and other things, and it turns out that people did a bunch of different variations of this experiment, and it turns out that if you sort of, instead of doing this abstract type of task, if you sort of make it more relevant to social situations, so there's a version where you're looking at, so there's a bar, and there are people in there drinking things, and you're trying to guess, you're trying to figure out if people are doing, like underage people are not drinking alcoholic beverages, let's say. And you say, it's like, I'm going to check the age of the person and what type of drink they're drinking. It turns out that more people are able to figure out the logical, what you should be doing logically compared to this abstract thing. But of course, in our situation, in this class, we're going to be doing abstract math stuff. And so that means that we're not going to have that social context to sort of guide us. There is some sort of intuition, of course, that I hope you'll be able to build in time, but still. Okay, any questions about this? I just wanted to mention this. It's a nice logical thing. And this implication stuff is sort of one of the things that we're going to be using in this class. Okay, so how to approach statements in math 3210. And in no particular order, I said over there. Because when you see an exercise, or when you see a problem in a problem set, or a problem in question in an exam, I'm not going to necessarily tell you that prove this, okay? What I'm going to say is that I'm going to give you a statement, and your job, first of all, is going to be to figure out if it is correct. I'm not going to tell you it is correct. And so I thought about this, I guess 4 or 5 step program. But I'm saying in no particular order because, the cognitive processes associated to doing math is somewhat complicated, and it's beyond my pay grade as well. So you want to be able to do the following things. You want to figure out, first of all, if it is true or not. Now, maybe it is actually true, or maybe there's a typo, maybe there's a mistake. Maybe the author of the statement that you're reading just missed a detail, or maybe they weren't that careful about the details and stuff like that, right? So these are important things, and if possible, you want to be sure. If not, you at least want to have a guess, okay? Possibly, let's say, with some probability. Okay. So maybe you're going to encounter certain statements that you cannot really distinguish at a certain time, whether or not they're true. But at the very least, you want to have some guess. You want to say, okay, 70%, I am 70% sure that this is correct. There's also a theory of what it means to prove things probabilistically, especially in computer science. This is an important thing, but we're not going to get there. Another thing you want to do is, of course, build your case, okay? So you have a statement, you see a statement. Build a case. When you see this abstract statement, you want to start thinking about examples, non-examples, counterexamples, non-counterexamples, okay? So come up with examples, non-examples. And I'm going to leave it to you to figure out what I mean by a non-example. Counterexample, examples, counterexamples, non-counterexamples. Further, sometimes maybe you can't even do this. For instance, in the case of proving that root 2 is not an integer, not a rational number. Well, what you can do is you can start a proof. Okay, we're going to learn a couple different methods. You can start a proof, and you can try to sort of keep pushing and pushing, and maybe you're going to get stuck somewhere. And then where you get stuck in the proof is going to tell you something about whether or not the statement is actually true. Because ultimately, if something is false, you cannot prove it, but you can still try to prove it. And ultimately, you're going to get stuck if it's false, really. I mean, you might get stuck. Of course, you can always prove something that is false, or you can always convince yourself that you're proving something false, but that's up to you in a sense. Start a proof and see if you get stuck somewhere. And this is going to happen quite often. You're going to start a proof because you're sort of like you convince yourself that something is the case, and you start a proof, and then eventually you're stuck in, like, you cannot see how you can go further. And then something's going to happen in your mind, quite possibly, and you're going to say, oh, silly me. Clearly there's a counterexample to this, and here's a counterexample. This is not the end. 4 is what I call 3. Okay, 3 is prove everything. Everything unless it was covered in class or in the textbook, right? Those you can take. Everything else, you prove. There's item 4, so I want to leave it there. I'll write item 4 after deleting this, actually. It's sort of like a next step. In class, or in the textbook. The textbook by Joe Taylor. No bluffs, okay? I will call your bluffs. So what do I mean by this? Well, statements like, clearly this is the case, it's obvious, it's trivial. I mean, it might well be, but you might be bluffing. So if you say something like that, probably I'm going to be like, I think you should prove it. Clear, trivial. In other less incendiary phrases, it can be proven. You see this typically in calculus books. General statement, general idea is, when in doubt, prove it. It's like you think about, oh, there's a step. Should I prove it? Yeah, you should prove it. So generally speaking, you should always think of the following, right? Like there's this game. It's like you start with a statement. I don't know. It's like when it's cold, a lake, let's say, starts freezing from the top. And then you say why. And then you keep asking why and why and why. And because it's like, the density of ice is less and blah, 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 right? You can always keep asking why. And in math, too, in principle, you can always do this. Now, whether or not you should be doing it all the time, that's a different matter. But that's sort of like the general idea. OK, any questions so far? Now, 4 is what I call logical perturbation. Now that you're done with the statements, it's never over. OK, math is never over. So there's a distinction when it comes to games. They say there's finite games and infinite games, and finite games are things like chess. It's like you play and eventually there's a game over. Math is not like that. Math is a game that you keep playing. You play it to keep playing. Of course, there are restrictions because this is a class and all that stuff, and we have only so much time and so much. You also have so much time, but still. Logical perturbation is about the following. You take a statement, let's say that you understood everything, or maybe you haven't, you see, in no particular order, but you start sort of changing the statement a little bit. You start perturbing the statement logically speaking. So for instance, in the exercise that root 2 is not a rational number, I can think about, oh, what is it about 2 there that really sort of helps me in the proof, right? Maybe root 3. A similar argument could possibly work there. Or maybe I can try for root 6. See, that's sort of like generalization. So there are a couple different ways of doing this. And let me write these down. Well, yeah, I'll write it here. So first of all, you can try to weaken the statement, hypotheses. So can you still prove the same conclusion without assuming as much? So you can be more frugal. Weaken the hypotheses. Or you can try to be more greedy. With the same hypotheses, can you prove something stronger? strengthen the conclusions. What else? Well, maybe you can try assuming more. So maybe you cannot prove this general statement, but maybe you can prove a more simple statement, more restricted statement. But maybe you can get more, okay? Because if you sort of decrease, if you make your scope smaller, typically that means that you have more properties, which is reasonable to expect then that you can prove more. Assuming more, can you prove more? Can you prove more? And another thing, of course, is can you come up with other proofs? Often there are multiple ways of doing the same thing. And these multiple ways are not necessarily logically equivalent. Okay? There are logical equivalences like this contraposition that I mentioned a while ago. But sometimes there are really mathematically or logically different ways of approaching things. Are there other proofs? Maybe simpler proofs. Maybe more complicated but more concrete proofs and stuff like that. Okay? This is sort of the general scheme that you should use when approaching statements in this class. Any questions about these? Okay. So we were talking about sets. Now that this is done, let me give another class of sets that we're going to be using quite a bit, which are what are called intervals. These are subsets of the real line. So let me also introduce these two symbols. One of them I started using yesterday, I think. So this is going to stand for lowercase a is an element of uppercase A. So here, lowercase a is a point or an object, let's say, and uppercase A is a collection, is a set. Okay. Another thing is the following. When I write like this, and this is going to stand for uppercase A is a subset of uppercase B. So in this case, both of them are sets. So in terms of Venn diagrams, let's say, the first one you should think of it like this. So you have a blob like this, that's A, and in it there's a point, which is lowercase a. The other one is more like this. This is uppercase B, and then here is uppercase A. Okay? Again, I don't want to talk too much about these things. We're going to keep using these symbols in this class. So intervals. So these are specific subsets of the real line. These are, in a sense, nice subsets of the real line. Which recall we denoted by this R in Blackboard bold. Okay, so I can be more abstract here, but let me just give specific examples. So for instance, 1, 2, and I'm going to use these square brackets. This means the set of all those numbers, rational or irrational, that is to say, any real number, that is between 1 and 2, endpoints included. So I can write it like this, using this set builder notation that we discussed yesterday, right? So I need to open braces, close braces, put a bar. To the left, I'm going to have to say something about the general form of the elements in the set. So let's use some letter, x. Sometimes you can also write it like this too. X in R such that this and then this. Okay, nothing too complicated. There's also the open interval. So this is what is called the closed interval. The open interval is the same thing, except that you don't include the endpoints. And here I'm going to use a notation that is different from the notation that is used in the book. So in the book, they use this notation. Let's use different numbers. 3 to pi. Pi, that, you know, the number, 3.14 blah, blah, blah. I'm going to use, again, closed braces, closed brackets, but I'm going to turn them the other way around. Okay, so this is what is called the French notation. People educated in France, I wasn't educated in France, but still I like using this. They like using this notation, and the more American notation is this, of course. Okay, I'm not going to use this because this looks like a pair. This looks like a point in the plane. This is more clear to me. And so what is this? This is a set of all those reals such that, well, x is strictly between 3 and pi. It's open interval. And the sort of intuition behind this notation is the following. So you're sort of imagining this something like a Lego piece. Okay, so let's say you have, well, let me just draw it. So here's 3, here's pi. Okay, and then this is a notation. The point being is that to the left of it, what you have is, let's say, minus infinity, comma, 3. What you see it is, so the braces are toward 3 here for this part. And this piece sort of, you can sort of join with this piece if you want it. That's sort of the intuition. Any questions about this? Is this too straightforward, too easy? Don't worry, things are going to get more complicated, but still. It's the second day of classes. Okay, so these are the two types of intervals. There are more, of course. You can do half open, half closed. Let's just write one of these. 7 to 9. So what does this signify?
So we have a closed interval on 9 and an open interval on 7.
Yeah, right. So all numbers between 7 and 9, 9 included.
9 included.
Exactly. So this. Sometimes people also use this notation, by the way, to emphasize that you're not including this. So it's a strict inequality. And like so. Okay, and there's a bunch of other things, but these are sort of the standard things. Any questions about these so far? Okay, set operations. I'm just going to use intervals because it's more concrete. Set operations. Let me just list them down, and then we can write down a couple examples. So what we have are the following. We have this, then this, and then this, and then I wrote subset, but still it's good. So this stands for intersection, and the way you should think about it is that there's an n here, see it's coming down. This stands for a union, U. This is what is called symmetric difference or symmetric union. This is the complement. And this is subset of course. In a second, I'm going to give examples of these. Now, these are somewhat, they correspond, each of these corresponds to a certain logical operation that we talked about before. So maybe I can ask you, can you come up with a logical operation that corresponds to intersection?
And?
Yeah, right. How about union? Or, exactly. Maybe this is hard to see, but this is going to be XOR, exclusive OR. So this is exclusive OR. So this is something like the following. So you want to say, oh, I'm taking linear algebra, or so let's say the following. Let's say that this set corresponds to this set represents the students who are taking linear algebra. And then this set represents the students who are taking differential equations. Let's say it's a different class. And so the students who are taking linear algebra or differential equations is the whole thing, okay? Whereas the students who are taking linear algebra XOR differential equations is not the whole thing. It's the students who are taking linear algebra but not differential equations, and differential equations but not linear algebra. Okay, so you sort of get rid of the intersection there. How about complements? What is the logical operation that corresponds to complements? Yeah. How about this subset of? There's a logical operation, it turns out, that corresponds to the operation of, or relation of, being a subset. So something like this. Imagine, let's say that, so you see the smaller blob is a subset of the larger blob. That means that if someone is in the smaller blob, it's also in the larger blob. So this corresponds to implies. Okay. I know this is somewhat more abstract. Let's get more concrete and give examples of these. So for instance, I'm just going to use intervals for all of this. Let's start with 1, 2. In fact, let me delete this as well. Okay. Now, what I can do is the following. Instead of writing two inequalities like this, I can use the connector AND. So I can say this is equal to the set of all those x's such that x is not less than 1 and x is not greater than 2. So okay. I mean, writing this literally means the same thing as this. But when you have this, this is the same thing as saying this is the intersection, this set is the intersection of x such that x is not less than 1, intersection, x such that x is not greater than 2. So this is what I mean when I say intersection in terms of set operations correspond to and in terms of logical operations. Inside the braces, I had the logical operation, and then I was able to, in a sense, distribute, right? And turn this logical operation into an intersection. Is this clear? This is a silly thing in a sense. I'm just like rewriting the same thing, but it's going to be very, very helpful. And then I can go further and use the following notation for these two. And even though these are sort of open-ended in a sense, I still want to think of them as intervals, so I'm going to write them like this. So this is the first piece. 1 to infinity. Infinity, you see, not included. Later on, I think we're going to discuss a little bit what is called the extended reals, where you get to pretend that this infinity is a number as well. Okay, intersection, and then minus infinity to 2. Okay, so this set is the intersection of this and this set. Any questions about this? Okay, so let's look at an example with a union. Well, let's still stick to 1 over 1 comma 2. So I want to write 1 comma 2 as a union of two things, let's say. So that's the first example. The next example is the following. 1 comma 2. Well, I can chop it in half somewhere, let's say 1.5, and I can write it like this. Okay. So visually, what is happening here is the following. You have this interval from 1 to 2. That means that you have every single number in between. And I, randomly chose 1.5. So it's here. Now, what does this notation mean? It means that I'm looking at all the numbers between 1 and 1/2. 1 is included, 1/2 is not included. If it's not included here, I must include it there. And I hope this sort of graphical sort of thing also makes sense. This is sort of like a Lego piece, you see. You can sort of like join these two things and you get this thing. Okay? And so this is 1.5, and you're not including it on the left side, which means that you have to include it on the right side. Does this make sense? Of course, this is not unique, right? Like I can keep going like this. And when we start talking about integrals, for instance, this partitioning an interval is going to be an important thing. One thing I can do, for instance, here, I can do the following. Oh, sorry. 1, and then this, and then let's say that I didn't include it there either. Well, I can just add it as an additional set. It's the same thing. The order in which you write these things doesn't matter, okay? And that's one of the important things about set operations. Does this make sense? Okay. Symmetric union. So for instance, let's look at the symmetric union, symmetric difference, should be. It turns out that you can really think of this as subtraction. Let's look at 1, 3, closed interval, symmetric difference, 2, 4. Now, when I have this, I want to have all those numbers that are in either this but not this, or in this but not that. So what is the intersection here? Let's draw it. So 1, 2, 3, 4. So the first interval is this. The second interval is this. Okay. I'm looking at exclusive OR. Well, that means that I need to get rid of this middle piece, the intersecting piece. So it's going to be 1, 2, and then 3, 4. Okay. Yes?
Since 3 and 2 are inclusive in that, does that mean they shouldn't be in the union?
You're right. Thank you. What your colleague is correctly correcting me is that the intersection here has the point 2 in it, right? Because 2 is in this part, and also it's in this part, which means that it cannot be in the XOR part. Okay, does this make sense? Okay, complement. Well, maybe let's write it like this. 1 to infinity, let's say 1 included, to the c. That's the notation. There's another notation, which is this. You write the name of the larger sets, and then you put a slash, and then you write the set. So this is the set of all those points in the reals that are not in this set, which means this should be the following. What is remaining? See, this is the missing Lego piece. If you have the whole real line, and if you were to take out this Lego piece, you're left with this Lego piece. Okay? And then finally, maybe let's write something for subset. 1, 2, well, open is a subset of 1, 2 closed. Okay. Now, how do you interpret this from a logical point of view? If you want to think of this logically, what this is saying is the following silly statement, really. If I have a number that is strictly between 1 and 2, it could also be equal to 1 or 2. Obviously, that's not going to happen, but if it's here, that's satisfied also. That is to say, you can always relax strict inequalities to non-strict inequalities. Well, that is not always true. In this case, it is true, but it's not always true. So I'm not going to write it. Okay. So that's all there is to know about sets. I want to talk about something called Cartesian product and relation. And then we're going to be able to start talking about functions. I don't want to push it, though. So I think it's a good place to stop today. Thank you. I'll see you tomorrow. Okay, good morning. So today we're going to keep working on set theory stuff, certain constructions that we're going to use throughout this class. But before that, I wanted to mention this. At the end of last class, one of your colleagues came to me and mentioned the following, that in the textbook that they were looking into as well, the notation that they use for A being a subset of B is this instead of this. Okay, and so recall this was the notation that I introduced yesterday. So this stood for A and B are subsets, A and B are sets, and A is a subset of B. So and the picture was this, right? So we have this larger blob that I call B, and in it there's a smaller blob. Maybe it has multiple parts and stuff like that, but for visualization purposes, it's nice to do this. Now, the reason why I use this notation as opposed to this, the idea is that I'm sort of thinking of this in analogy with this less than or equal to sign when it comes to numbers. Okay, so this is kind of like this. Now, in the book, they mean exactly the same thing as this when they use this notation, but I'm never going to use this notation. Okay. I'm always going to put this, and the difference here is the following. Just like here, you have a strict inequality. Remember from yesterday that I said sometimes people write this, and they put sort of like a dash, so they cross the sort of the equal part of this symbol to signify that it's a strict inequality. And likewise, here this is going to represent a strict subset. So in this case, A might well be the same thing as B. So let me write it in this notation. A might be equal to B. And of course, let's also mention what it means for two sets to be equal. Well, two sets are equal if any element in one of them is an element in the other one, and vice versa. Right? So sets are supposed to be mathematical objects that are amorphous. They don't have any structure whatsoever. Later on, we're going to learn certain structures, topological or continuous structure, and then the smooth structure. But when it comes to sets, they are defined precisely by what is in them and what is not in them. Okay, so maybe I should give an example here as well. So I can write something like this. So for instance, R is a subset of itself. It's more, of course, R is equal to itself, but certainly this is also true. And let me perhaps write this as well. This is false, okay? Because this is saying this thing is a what is called proper subset. It's a subset, but it is not equal to. Okay, so this is a false statement. Any questions about this? Now, there is a further, perhaps more philosophical question. Now, if it is the case that in the textbook they are using this notation, why am I using this notation? Right? Well, I kind of mentioned why. This is sort of the idea, because I'm using this symbol in analogy with this less than or equal to sign. Another thing, too, of course, is the fact that this or some other notation, these are not universal notations, okay? So from textbook to textbook, it changes. And often from field to field, it changes also. And so this is also part of developing this mathematical maturity. So, so one of the issues with sort of sticking to one textbook is that it gives a false sense of security when it comes to what people call things, how people denote things, and so on. And then you overfit your understanding, right? So you're sort of like trying to understand something, and then you overspecify. And then you go out into the real world, and let's say you're trying to do some engineering problem or some other mathematical thing, let's say, and then you come across a paper, another book, and so on, and then you realize you cannot read it because none of the symbols are similar or familiar to you. And I'm trying to combat that from the get-go. And you know, it is the case that in mathematics or in so whenever you're looking into something that uses mathematics, engineering, physics, and all that stuff, it turns out that different people call same things different names, and sometimes different things the same thing. Okay, so it depends on the context and stuff like that. So I just want to prepare you about this. Of course, it makes things a little bit more complicated, but I think it is worthwhile. Any questions about this? Now, then there's the question of, oh, if that is the case, should I even be looking into the textbook? I would say yes. I would say try reading the textbook. Of course, you're going to have to come to the classes also because we're grading the attendances. And try to reconcile all the time the things that are done in the textbook and the way I'm doing things. So here, this was an instance of notation being different. Later on, starting from next week, in fact, we're going to have even more dramatic discrepancies. One of them will be the following. So for instance, in the textbook, they spend a lot of time building the axioms and proving things from bottom up and stuff like that. I'm not going to spend that much time. I'm just going to say a lot of things. I'm just going to take a lot of things as axioms because I'd rather spend more time proving things about integrals and derivatives and other things. And so you're going to see things that I just say as axioms. I just state as axioms in class. But in the textbook, they're just like trying to prove it and stuff like that. So that's also part of this exercise about reconciling two accounts. And this is also the thing that's sort of like a standard thing when it comes to mathematics. You see in one book an exercise, and it turns out that the exercise in one book is actually the definition in the other book, and so on. So there's no unified account of things. And you should get used to these things. That's all I wanted to say about this. Any questions about this? Okay. Okay. So I'd like to mention 3 ways of building new sets out of old ones. And there are certain levels at which you can discuss these things. I'm going to not go too much into detail. I'm not going to try to be too formal about these things. I'm just going to define them, and we're going to be on our way. So the first method is what is called Cartesian product. Okay. So this is a way of multiplying sets. Cartesian because allegedly Descartes, one of the sort of modern philosophers, or probably the first modern philosophers, if you ask some people, he was the one who realized that, if you have an input-output relation, well, what you can do is you can turn it into a coordinate system and sort of draw things in a plane. And so that's why it is called the Cartesian product. The second is what is called powerset. And this is sort of like a method of going to the meta. I'm going to discuss what that means in a second. And then the third one is looking at a set of functions, or sets of functions between sets. Okay, it's going to be another set, of course, but its elements are going to be, it's going to be important to think of the elements of the set as not only points, but also things that you can graph. And this is where things are starting to get a little bit more abstract, of course. So, method 1. So, maybe I should say just definition. Let x and y be sets. Then their Cartesian product is defined as follows. Is defined to be the following set. I'm going to denote it by x times y, or x cross y. And this will be the set of all those pairs such that the first element in the pair comes from x and the second element comes from y. And so I can use this set builder notation. Okay. Open curly braces, and then bar, and then close curly braces. Here I need to write down the typical form. So it's going to be lowercase x, comma, lowercase y, in parentheses. So whenever I write it like this, this is an ordered tuple. Okay. Such that on the right-hand side, I need to write down the condition. X, lowercase x, comes from uppercase x, and lowercase y comes from uppercase y. Okay. What's the first example? Of course, Euclidean spaces, or powers of R. So this was the first method. Let me just write it here. So for instance, what you would denote by r to the 2, right, the plane, well, this is nothing but r times r. So in a sense, this is r squared. That's sort of the idea. Any questions about this? Yes.
So is it genuinely a cross product or just multiplication?
It's, I mean, you mean in terms of vectors?
Yeah.
No, it's not a vector. It's not a cross product that you would learn in multivariable calculus, but it is denoted by a cross.
It is a new third thing that we're using the little cross for.
Yeah, I mean, there are only so many symbols, right? And I mean, yeah, there's this thing. There's this constant struggle because there are only so many things, so many symbols. And so when you try to represent a certain operation, either you're going to use something that was used to sort of like signify, oh, it is like this. It's like I'm just multiplying r by itself and I get the r squared. Or sometimes you want to say, oh, but it's not exactly like this. And that's why, for instance, there are similar symbols where you put things like cross, but in a circle and stuff like that. This is what is called the tensor product. It's like, it's just a product. But this is fairly universal, this notation. Okay. Any other questions about this? Okay. Okay, so that's the first method. Second method is what is called the power set. Let X be a set. Then its power set, which is denoted by P of X, is the set of all of X's subsets. Okay, and so things are getting complicated here. Then its power set is defined to be the following set. So I'm going to denote it by P of X. So I like to use this curly P of X equals, so how do I write this? Again, I can use the set builder notation. Typical element is A, and the condition is A is a subset of X. Okay? So this means that using this power set operation, you can relate this element of relation that we discussed yesterday and the subset of relation. And so, thus, A is a subset of X. Here's a new symbol. This is how I'm going to read this is I'm going to say if and only if it is equivalent. So it implies this side and this implies this side. This if and only if A is an element of X, of P of X. Let's do an example. And in a second, I would like to say, make a comment about why it's called a power set as well. So here's an example. When you're trying to understand these kind of things, it's nice to think about a finite set. Okay? So for instance, let's look at this. Let me let X to be the set consisting of two things, two letters, A and B. What is its power set? Its power set is supposed to be the set of all subsets in X. Okay, so I need to list all of them. So then P of X is, well, I need to start with what is called emptysets. This is a silly math thing, but you have to include the thing that is the most, basic, most obvious thing. This, so all with a dash. This is the empty set. Empty set has nothing in it. And then you have a set that consists only of A, another set that consists only of B, and then X itself. Okay, so maybe I should denote it here. Oh, okay. Yeah, sorry. I'll be more careful going forward. So here, this thing is, it stands for empty set or the null set and stuff. And how do you denote this? Well, you just open braces and close braces without writing anything inside. Okay? Any questions about this? Yes?
Why are we not including a set of all B's?
Yeah, maybe. Yeah, sorry. But you're right. You include all of them. And you see the interesting thing here is that this set X is an element in P of X. Now, why is P of X called the power set? Well, you look at how the number of things in the set change, okay? So for instance, in this case, X has 2 elements, and P of X has 4 elements. Okay, so if I had 3 elements in X, let's say X consists of A, B, and C, how many elements do you think would P of X, how many elements do you think would it have? Yeah.
I have a different question.
Yes.
Can we replace X with the AB just as the one element? Like, could we write it differently and write the empty set?
Exactly.
And then AB?
Exactly. That's a good point. So maybe I should rewrite it here. This is the same thing as writing. Oh. Writing this, okay? Now, why is that? Well, it's because X, this capital X, is literally the same thing as this. And when it comes to sets, like they're the same thing. So you can just substitute whenever you see one instead of the other one. I was just being lazy. Okay. Okay, so back to the question. Let's say that X, capital X, has 3 elements. How many elements does P of X have?
8.
Yes, right? So I'm going to leave that as an exercise. That's a good point. If it is not clear to you, what you should do is you should write it out explicitly. It's going to be painful, but it is useful. Okay? Write it out explicitly. List all of the elements. Exercise. Let me write it like this. Number of things in X, I'm just going to denote it by this, implies what is 8, of course? Let's do some numerology. How do you relate 8 to 3? It is 2 to the 3. Let's write it like that. And so this is my notation for number of things in X, number of elements. Okay. You can write it out explicitly. Say X contains A, B, and C. Write all of the elements. The main idea is the following in this calculation. And this is going to lead to the next exercise. And when I'm giving these exercises, insofar as they're not in the problem sets, you don't need to turn it in. Okay? So these are just things for you to think about. But of course, I might sort of think about them and put them in the problem set. So it is in your benefit, it's beneficial for you to think about them, just in case, and they might show up in the exam as well. The idea is this. Let's say you start with your capital X, that's your initial set. Now you're trying to understand the power set of it. So an element in P of X is a subset in X. How do you build a subset in X? Well, you look at any element in X and you decide, is this element going to be in my subset or not? Okay, so that means that for any element in X, you have two choices. Either you include it or you don't in the subset. And based on that, you have 2 times 2 times 2, ultimately. And in fact, it turns out that this is more generally true. This is equal to 2 to the number of things in X. And this is why it's called the power set. I mean, presumably, I don't know why it is called power set, but this seems to be like one way you could justify. Okay? Now, it turns out that this equation is true even when X is not a finite set. So maybe you want to take X to be the set of integers, which is an infinite set. And then, okay, so it's kind of dubious what it means. It's kind of dubious to use the word number of things when it comes to an infinite set. And that's why people use this phrase called cardinality. So if you want to be more proper, you say cardinality. And it turns out that, for instance, in a sense, the number of subsets of the integers is 2 to the infinity many, where infinity is the number of integers. And there are different types of infinities and stuff like that. We're not going to spend that much time on this stuff, but it turns out that it is somewhat useful. Maybe if it turns out that we're going to use them, we might sort of discuss it a little bit more, but it turns out, let me just leave it at that for now. There are different types of infinities and all that stuff. Okay, any questions about this? Okay. Good. So next up, there's a third method. But for that, to discuss the third method, I need to tell you what the function is. And even before that, I want to do something slightly different, and I want to discuss this other notion, which is more general than a function. It's called a relation. How many of you have heard this term, relation? Okay. A couple of you. Okay. So, well, maybe I should ask as well, how many of you have heard the term function? Okay, you took calculus after all. Okay. Now, the notion of a relation is a notion that is more relaxed relative to the notion of a function, and it's all over the place. Okay, and it's good to see it at least once. And we're going to use it later as well, so we might as well talk about it now that we're talking about the foundations and all that. Let x and y be two sets. And of course, I might as well, I can take them to be the same set, but I don't need to. Then, now the definition is going to be very terse, okay? Then a relation from x to y to y is a subset of their Cartesian product. Is, by definition, in fact, let me do this. I'm not going to keep writing by definition whenever I underline a phrase in a sentence. That means that I'm defining that phrase. Is a subset of x times y. In other words, so aka R is a relation from x to y if and only if R is an element of the power set of x times y. Okay. Examples. Let's start like this. I want to be concrete here. Let's take x to be the unit interval, closed interval from 0 to 1. And I'm going to take y to be the same thing. The benefit of doing this, of course, is that I can also draw it, right? So I'm going to give a couple examples here. Let me take x and y to be both 0, 1. I can certainly do this. Now, what is x times y? Geometrically speaking. So if both of these sets is a line segment, what is x times y? Yeah, it's a square. So how would you write this? This is, if I were to substitute 0, 1 instead of x and y, this is how you would write. And of course, if you wanted to draw these, what you would do is the following. Here is both x and y, and x times y is just this guy. Okay, now when I'm talking about a relation on x, I'm not going to say y because they're the same thing. I said that a relation is a subset of the cross product, of the Cartesian product. That is to say, a relation R is going to be a subset of this square. Well, geometrically speaking, a subset is just a shape. So a relation on x is a shape in the square. So this is your heuristic. Okay, so for instance, here's one relation. Okay, so this is a subset of x times x, which means that a typical element in R is a pair of numbers. And also note that even though we're looking into single variable calculus in this class, immediately we have two variables. And in fact, we're going to have infinite dimensions when we start looking into this function space. Okay, so let me define R to be the following. X comma y such that x is less than or equal to y. Is this a subset? Certainly it is. It is well defined, and I can even draw it. And in fact, probably some of you are familiar with this type of thing from integration and multivariable calculus and stuff. So how would I draw this? Well, here's my square. Here's my main diagonal. So x is supposed to be the horizontal variable in this representation, and y is supposed to be the vertical. Why is it that way, and what is the formalism behind it? I mean, let's not get too much into these kind of things. It's clear that I'm sort of representing this as x and this as y. If you want to be more specific, you would just draw sort of like the axes and name the axes and so on. Okay. So certainly, the diagonal where x equals y should be included in my relation. So the main diagonal is inside. How about, so should I be including the upper triangle or the lower triangle? Upper? Why? Because, so let's test it out. So if I were to plug in x equals 1/2, which means that I'm testing this thing, well, I need to include in my relation all those y's that are equal or greater than 1/2, which means that in this vertical slice, I should be including the top part. Okay, which means that I should be including this triangle over here. Any questions about this? Now, in this case, things are rather perhaps obvious, but even when you do more and more abstract stuff, it's good to be able to switch from this sort of syntactic notation to some picture, some caricature, and vice versa and stuff. And in fact, you see, I can think of this, which is a relation itself. So this I want to think of as a relation in and of itself. I can think of it as a subset. I can think of something that relates to things, and I can think of it geometrically. So this is an important thing to be able to do. Okay, so this, I would say, is the less than or equal to relation. Less than or equal to relation. Any questions about this? Okay. So let's get a little bit more abstract. Can I think of the notion of something being an element of something else as a relation within this formalism? Maybe even before that, let's do something more concrete again, based on calculus, and then we can look at that problem. So here's another thing. Now I'm going to take x and y to be r. So x times y is r squared, and here's a relation. X comma y such that x squared plus y squared equals 1. This is certainly a relation. How can I think of this geometrically? It's a circle, right? What you would say, what you would call a circle, it's a shape after all, is a relation. It's the unit circle. Okay. So in a sense, you were using relations all along, and you know that this is not a function. Well, maybe I should ask, how many of you know that this is not a function? How would you sort of justify it's not a function? There's like a test and stuff.
The vertical line test.
Yeah, right? So there's this thing called the vertical line test, which says that if you have a shape, a relation, it's a function, it defines a function if whenever you draw a vertical line, you hit whatever you drew at exactly one point. And in this case, you see, here's a line that hits the shape at 2 points. Now, if I were to use this other line, of course, it hits the shape at 1 point, but it doesn't matter. For the vertical line test, you should be hitting at exactly 1 point for any vertical line. Okay, so not a function, but it's a relation and so on. Now, if you're one of those who are going to take the the sequel to this class, it's the multivariable calculus version of this class. You're going to learn a theorem which is very important. It's called the Implicit Function Theorem, which tells you when you can in fact solve y for x. So for instance, in this case, what you can do is you can take, y is 1 minus x squared in square root, but then maybe plus square root minus square root. So it's not a function exactly, but maybe you can choose a plus at some point, and that kind of works and stuff like that. So you're going to get to the formalism behind it. For now, this is just where I want to leave it at. And there are many other things, of course, that you can do. Any questions about these things? So let's go back to this more abstract thing. I want to think of the element of relation. So what do I need to do? I need to do something like the following. So I want the following to make sense. So here's the set builder notation again. You see, this is an important thing to be able to do. And a lot of people, for instance, people who are doing physics are very good at these kind of things, at least good ones. They take a mathematical formalism and they overload it without worrying too much about whether or not it makes sense. And then they figure out that it makes sense, or they leave it to someone else to make sense of it. So I can just keep following the set builder notation and see if I can make sense of it, okay? So I want to say, similar to this situation over here, but I want to use the element of relation. Okay? So substituting everything, just, without thinking too much, instead of x here, I see a lowercase a. So instead of x here, I should be seeing a lowercase a, and instead of y, I should be seeing an uppercase a. So that means that I should be thinking of it like this, which means that the first set here should be some set x, second should be its power set. So this is a relation from x, a set x, to p of x. X times p of x certainly is valid because I can take the Cartesian product of any two sets whatsoever. So it's all good. Now it turns out that if you keep pushing these things, and if you keep sort of building these self-referential things, and if you keep sort of using these operations in conjunction too many times, for instance, you can look at p of x, which is valid. Eventually, it turns out that you can break math. There's a bunch of bugs and stuff. And that's why there's a bunch of words about, like sets. Instead of saying set of sets, you say collection of sets and stuff like that. Let's not get into that. Back in, let's say, the 20th century, last century, people were very worried about these kind of things, the foundations of math and stuff like that. Nowadays, especially from a more pragmatic point of view, we realize that, okay, so if you push it too much, you're going to break it. But don't push it too much, then it's like, it is not limitless. We just know that. And when it comes to using math or proving the types of things that we're going to prove, it's not going to be too much of a problem. But there are sort of like certain issues underneath. Okay. Now similarly, even before this, maybe I should leave it as an exercise to try to visualize this element of relation for our set let's say A, B, C. Let's leave it simple, actually. And let's say capital A is, well, the set that contains only A. Try to visualize this guy. Exercise is that. Oh, I guess I need to not fix uppercase A, sorry. Now, how can I start doing this? Well, I need to somehow draw x times p of x. Well, these are finite sets in this case, so I can just, put a bunch of points. So this is the first coordinate. X has 2 things. And then p of x has 4 things, which means it's going to be, or it's going to be something like this, right? So so each of these corners represent 1 point. And then you can draw this element of relation. Okay, so of course you need to label these terms and stuff like that. Okay, you see, you take this idea of being able to think of something geometrically and you apply it to something more abstract. Still, it's not very abstract, but still, it's non-trivial to go from this to this. Okay, but it is very useful to be able to do. Any questions about? Yes.
Is what you've drawn a Cartesian plane?
No. I mean, if you want to be perhaps more accurate, you don't want to put the lines there, but putting the lines there is easier to sort of draw. Because in this case, x times p of x is just going to be a bunch of points. And we haven't talked about this, but like I said before, sets are supposed to be amorphous things. So for instance, when I'm drawing this picture, I'm in fact assuming certain structure that allows me to actually take this syntactic representation and draw it like this. So it's a vector space, blah, blah, blah. There's a bunch of things that I'm saying, that I'm doing. Okay. In this case, in this more abstract example, there are no sort of structures like that, but still I can pretend that there is some structure, just to visualize. Okay. Any other questions? Now, here's a definition. And this is going to lead to the third way of defining a new set. I'm going to say that a relation is the graph of a function if a certain thing happens. Well, I'm just going to take this idea of this vertical line set and abstract it out. Let x and y be sets, R be a relation from x to y. You see, instead of writing it out like that, I can just use a notation to just compress things. I'm going to say that R is the graph of a function if the following happens. R is said to be the graph of a function. So So you see here I'm defining what it means for a relation to be the graph of a function. I'm not still defining what it means for something to be a function. That's a different thing. If for any two pairs of points, for any x1, y1, and x2, y2, in R, okay, recall this meant for any. I'm taking two arbitrary points, and this is supposed to be 2. If the x coordinates are the same, then the y coordinates have to be the same too. So if x1 equals x2, then I want y1 to be equal to y2. That's the condition that tells you when a relation is a graph of a function. Okay? Yeah.
Shouldn't that work the other way as well?
No. So for instance, think of it like this. It's a constant function. Constant functions are functions. It's a relation, of course, but that's fine. Now, whether or not it is injective or one-to-one is a different matter, which we're going to get to. But I think I'm out of time. So we're going to stop here. And on Friday, I'm going to define what it means for what a function is, and we're going to continue. Thank you. OK, let's start. Good morning. So we have a lot to do today. We were talking about relations, and then last time I talked about a condition that tells you when a relation is the graph of a function, and we're going to get to that, which was also related to this idea of constructing new sets out of old ones. But before that, I want to do some other things, and then we're going to continue. So first of all, first problem set is up on Canvas. So right now, if you go to Canvas and if you click the assignment page for problem set 1, there you're going to see a PDF file, which you can download if you want, and so on. So you should read through it, and I should mention something, and I think I'm going to say a couple more words about problem sets and how you should approach them, and what should be your weekly workflow and stuff like that. But for now, let's just say it like this. The way I designed this class is so that it's a cyclical thing. It's an obvious thing, of course, but sometimes it's sort of like it becomes hard to keep track of the cycle. Okay? So the cycle starts on a Friday, which is today, let's say, and then it continues, right? So tomorrow is Saturday, and then Sunday, and then Monday, Tuesday, Wednesday, Thursday, and then Friday next week. So and like I said before, typically you're going to have some assignment due each Friday. Either it's going to be a problem set, or it's going to be a midterm, or an exam, or a final. And for a problem set, you're going to have basically a week to work on. Right, so I uploaded problem set 1 today. In later weeks, I might upload the problem set later in the day, but it's going to be certainly before the day ends. And then you're going to have a whole week, and then next week on Friday at midnight is going to be the deadline. Now, we talked about how the workload for this class is 8 to 12 hours, but there is in fact more to that, in that somehow, especially when it comes to learning math, having one large chunk of 10 hours turns out to be not the same as having multiple chunks, let's say 5 chunks of each of 2 hours. Okay? So I would highly recommend that you at least have a look at the problem set the day it is uploaded. Start tomorrow. Okay? Don't leave it to the last day. I'm designing the problem sets in such a way that it's going to be overwhelming if you try to do it in one sitting. Okay, I'm designing it so that every single day you work a little bit, and then initially maybe things don't make sense, and then you keep working on it. Let's say Saturday, Sunday, maybe you start sending emails to me, or you start going to the tutor center and stuff like that. And then let's say on Wednesday you go to the tutor center, and then on Thursday you work on it a little bit, and then on Friday you finally finish the problem set and so on. Okay, so this is very important. Don't leave it to Thursday, Wednesday, blah, blah, blah. Start today, if not tomorrow. Okay? So that's an important aspect. Another thing, and once you spend some time on problem set 1, I think on Monday I'm going to say a couple more words about it. So before going into these relations and what you can do with them and functions and so on, I wanted to mention these proof methods because you're going to need these. And it's kind of a bizarre thing to talk about how to prove things. And typically, it's like people talk about these different types of proofs, but in reality, it's not as straightforward to distinguish this proof from that other proof. But at the very least, I thought it would be a good idea to give you the general form, the logical form of each of these types of argumentation, and then start with a very rather straightforward claim about divisibility of numbers and sort of prove that statement using every single one of them so that we have an idea as to how this would work. But before continuing, are there any questions? By the way, that seat might be not a good seat because you cannot see me here. I mean, you can see me here, but not the stuff here. Unfortunately, I thought about it. I thought about whether or not I should just not write things here, but we have so little space that I'm just going to blame the design of the room. Okay? They should have put the board over there, I think, instead of here. Anyway, okay. So the statement I want to think about is the following. I'm just going to call it claim. Okay, there's a bunch of sort of words in math speak, let's say, that sort of like signify something that is claimed to be proven and something like that. You could see claim, proof, corollary, lemma, proposition, blah, blah, blah. Result. These are all like words. I'm just going to leave it as claim for now. There's a certain rhetoric going on, of course, when you call the fundamental theorem of calculus the fundamental theorem of calculus instead of the fundamental claim of calculus. Okay, claim is the following. Let n be an integer. It's a number. The claim is if n is odd, then 3n plus 7 is even. Integer. If n is odd, then 3n plus 7 is even. So that's the claim. Nothing too crazy about it, of course. You have an odd number, you multiply it by another odd number, that's again odd, and then you add yet another odd number, that gives you an even number. Fine. But the point of this thing is to give sort of like some exposition of these things, these proof methods. Do I want to say anything before that? Oh, let's do one thing. Let's try to turn this into logic. So let's try to sort of use the logical symbols in the set theory symbols. I'm going to write it in two different ways that are equivalent. AKA, using logic, well, AKA, let me say it like this. So I can write it like so. For any n in Z, if n is odd, so how can I represent n being odd? Well, n being odd is the same thing as n is not even. In other words, it is not divisible by 2. Well, the notation for this turns out to be the following. So this represents 2 divides n, and you put a dash here, that represents not, so 2 doesn't divide n, implies 2 divides 3n plus 7. So I can represent the same statement like this. Any questions about this? Using set theory, I can, instead of sort of using these divisibility symbols, I can use sets and write it like so. Again, for any n in Z, any integer, if n is not in 2Z, it's a set. Well, what is the set? It's the set that represents even numbers. So maybe I should write it. Set of even numbers. If n is not there, then 3n plus 7 is in 2Z. Okay, I can write it like this as well. So these are all the same statements. Okay. And in problem set 1, 2, you're going to see some parts of certain problems where I describe something in plain English, and I ask you to rewrite it or express it using set theory. And then there's going to be some set theoretical sort of equation, and I'm going to there I'm asking you to sort of rewrite it or restate it using plain English. Okay. Questions about this so far? Okay. Direct proof is of the following form. You want to prove a statement of the form P implies Q. Now, in this case, really, there are like quantifiers and stuff like that, but let's not get into the sort of like the specifics of this. So you want to prove this. Maybe I should say you want to prove, well, for each of them, let's say, you want to prove P implies Q for 2 statements. For direct proof, assume P. You don't know if P is true necessarily, but you assume it. And then through some logical manipulations and some math stuff, you deduce Q. Okay, that's why it's called direct proof. Plus logic, plus math, somehow gives you Q. That's the general sort of structure of a direct proof. So here is how I would prove this using a direct proof. Now I'm going to assume the assumption, and I'm going to try to come up with this. Let me say this as well. I'm going to try to be rather strict when I'm writing these specific examples, but as the course progresses, I'm going to be more and more loose, and I'm going to sort of leave certain parts of proofs to you to finish. Okay. Let n be an integer, and suppose it is not, so it's not divisible by 2. What does this mean? This means that it's odd. In other words, there is some integer k such that n equals 2k plus 1. That's literally what it means for a number to be an odd number. Then there is a k integer such that n equals 2k plus 1. So when you divide n by 2, you have a remainder. And the only remainder that can be is 1 in this case, of course. Now I need to figure out something about this number. Then 3n plus 7, well, I can just substitute n equals 2k plus 1 for n here. And then consolidating, what do I get? 6k plus 3 plus 7 is 6k plus 10. And then I can factor out a 2, because this is equal to 2 times 3k plus 5. Now, k is an integer, you see. An integer times an integer is an integer. The sum of two integers is also an integer, which means that 3k plus 5 is an integer, this guy. In other words, this chain of equalities really tells me that this number is twice some integer. That is that is the definition of this being even. Okay, and that's the end of the proof. Now, typically you can just leave it like this, but it's sort of like good form to sort of signify that you finished the proof. So one thing people do is they put sort of like a square and stuff like that. Some people would like to write like QED. It stands for something Latin, which basically says that the proof is over. There's a bunch of other things you can do, like IMT, it's Miller time. I've seen GG, I've seen RIP Bozo, and other things. There's a bunch of things, okay? So you're just learning these kind of things, so you might as well just get it out of your system. Obviously, these are not professional things, but when you're young, when you're first learning these kind of things, you're excused. Okay, any questions about this? Obviously, in this case, things are rather straightforward. As we go further and further, proving things are going to be more and more complicated. I chose this statement because pretty much you don't need any calculus or anything advanced to go through this. So for instance, proving that root 2 is not a rational number is slightly more complicated of a proof. Still, it's not super complicated still, but you need something compared to this. Okay, so this is direct proof. Proof by contrapositive is the following. So again, you want to prove P implies Q. Now, instead of starting with P, you're gonna assume not Q. Okay. Now, let me not say too much about this, but it turns out that I think I mentioned this last time. P implies Q turns out to be logically equivalent to not P, not Q implies not P. So you want to assume not Q, and then plus logic, and then plus math, and then you want to show not Q. So let me write it. So for this, assume not Q, not Q. Oh, maybe I should write it like this. So this was my symbol for not, the complement. Plus logic, plus math, and then hopefully you're going to get not P as a conclusion. Okay. And these methods also have Latin names and stuff like that. Obviously, you don't need to know what they're called, but you need to be able to perform them. Okay, so let me just make some room here. And I'm going to delete these logical statements as well, or notational statements as well. I'm going to take the same claim, but the structure of my proof is going to be different this time. So now I want to prove the claim using this proof by contrapositive. Okay, so now I need to assume not this. So let n be an integer, and suppose that 3n plus 7 is not even. Right? I'm just negating the statement. Well, not even this is the same thing as odd. So let n be more concise. Suppose 3n plus 7 is not an element. Right? So element symbol, but I put a dash. That means not in. 2z is not an. So suppose that it's not an even number. Thus, again, I'm going to use the same trick. There's a number k such that 3n plus 7 equals 2k plus 1. Okay? Okay, so I'm going to try to solve for n here. Thus, well, let's do this. I don't want to divide by 3 here for some reason. You're going to see in a second. But I can send the 7 to the other side. Thus, 3n equals 2k plus 1 minus 7. And of course, as you're writing proofs and stuff like that, you don't need to sort of keep writing sort of these intermediate steps. But just because this is the first time we're writing proofs, I'm sort of being more explicit. Of course, this is the same thing as 2k minus 6, and then I can factor out the 2. Now, 3n then is an even number, right? Because k minus 6 is an integer. I'm saying that 3n is an even number. 3, say again?
Shouldn't it be k minus 3?
Yeah, thank you. Yeah, so I factored out a 2 here, and as your colleague suggests, there should be a 3. In any event, the argument still holds. K minus 3 is an integer, and I'm saying here that 3n, this integer, is an even number. Well, if the product of two numbers is divisible by 2, well, at least one of them has to be that way, which kind of looks like a gap here, which in a certain sense it is, but let's just hold on to that. Maybe I can write it like so. Since 3 is prime, it is not divisible by anything except 1 and 3, it must be the case that 2 is divisible by 2, n is divisible by 2. It must be the case n is divisible by 2. In other words, n is even. What did I do? Okay, that's good. In other words, n is, let me say, not odd. So I assumed the negation of the conclusion, and I was able to end up with the negation of the hypothesis. And so that's the proof by contrapositive. Any question about this? Now, I mentioned something about there being perhaps a gap in this step. Probably for this class, we can just say this we can assume. Okay? But if you wanted to prove it, any guesses as to how you would sort of justify this step, this sentence here? So I have two numbers. I'm saying if the product is even, at least one of them has to be even.
You would have to prove that, like, if 2 divides A, B, 2 must divide A or must divide B.
Yes. Ultimately, that's the statement I'm using. And it turns out that there's a certain fundamental theorem, not of calculus, of course, but of what is called arithmetic, which says that any integer has a unique prime factorization. And if you take an elementary number theory class, blah, 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 there you would be interested in these kind of proofs. But for this class, let's just leave it as is. Okay? So there's a possible gap here. And this is really one of the reasons why talking about proofs like this is kind of iffy, because we're not sort of trying to build all of math from nothing, basically. We're just sort of like assuming a bunch of things so that we can start learning calculus and start proving things in calculus. But even in general, you know, when you're practicing math, typically, for instance, even if you're doing pure math, it turns out that there's no such thing as 100% complete proof. Okay? What it is that when we're talking about proofs and when we're talking about rigor in math, we're really talking about arguments that can be, in principle, completed. Okay? There's always some amount of gap. So when we're talking about, oh, you took calculus before and you know how to compute things and you know certain definitions, and now we're going to do things more rigorously, we're really talking about something comparative. We're going to be more rigorous compared to what you did before, but not 100% rigorous. Okay? And of course, just because I'm leaving this as a gap, you see there's a difference. Even though I'm sort of like recognizing that maybe there's something here that I would need, I'm not really going into it. So it's going to be a good thing to be able to distinguish, where's the gap, if at all? And if there is a gap, and if someone asks me to prove it, how do I answer it? Okay? Any questions about this? And here's an interesting thing too. This first method is logically equivalent to the second method. Okay? But somehow, as you go through it, you see, mathematically, the second proof is more complicated. You need more things to do actuate the second method instead of the first method. And this is sort of one of the mysteries of math. It turns out that even though a bunch of things are logically equivalent, because ultimately, if something is a theorem, it's a tautology, is what a logician would say. Somehow, it turns out that for certain statements, applying this argument is much easier compared to this other argument, even though they are ultimately equivalent, of course. You're proving the same thing. Okay, so that's the second method. Third method is proof by contradiction. And in a sense, I would say this is the most, this is the method where you have the most amount of stuff to deal with, to play with. And this is also perhaps some sort of logical systems don't really accept this method. So it really is slightly easier compared to the other two. And so again, if I want to prove P implies Q, what I'm going to do here to prove it using contradiction is the following. I'm going to assume both P and not Q. And then I'm going to try to come up with something that is blatantly false. Assume P and not Q. And then plus logic plus math will hopefully lead you to something blatantly false. Something like 1 equals 0 or some other thing. Okay? And again, it turns out that from a logical point of view, the statement P implies Q is equivalent to the statement P implies Q is equivalent to the negation of this. So you're really assuming, you want to prove P implies Q, you say this doesn't work, and then you try to come up with certain things. Okay. But for now, let's just leave it like this. So proof by contradiction, same statement, goes like this. So I'm going to assume both things, both that n is odd and that 3n plus 7 is not even, okay? Let n be an integer. Suppose and if you want to sort of signify that you're using this method of contradiction, you can say something like, for a contradiction here, but I'm just going to not write it like that. Suppose n is odd and 3n plus 7 is not even. AKA that it is odd as well. Let me not write it. Okay. Thus, well, I'm just going to use the same trick. You see, ultimately, it's the same idea. I'm just taking this notion of being an odd or even integer and turning it into some expression, some mathematical expression that I can manipulate and do some algebra with. Thus, there are some numbers, k and l, such that n equals 2k plus 1 and 3n plus 7 equals 2l plus 1. Now here I need to choose two possibly distinct integers. At the very least, I should be using two different variables because it's quite possibly this k is not the same thing as this l. I'm not saying, I shouldn't be assuming, I shouldn't be claiming that n equals 3n plus 7 here. They are possibly different things. That's why I'm using different letters here. And so what do I need? What can I do here? I can just substitute n equals 2k plus 1 in this equation. I have two equations. Well, if you want, these are linear equations, if you know, and you can solve it, right? Thus, 2l plus 1 equals 3n plus 7. And then substituting, I have 3 times 2k plus 1 plus 7, which then consolidating gives me 6k plus 3 plus 7, which we had before already, which is 6k plus 10. Okay. What to do here? So I'm trying to come up with something wrong, okay? Something has to break. Well, one thing I can do is the following. I can solve, I can collect the constant terms on one side and the variable terms on the other side. So this would give me the following. So 2L minus 6K. Oh, maybe I should write it the other way around. So I'm going to send 1 to the other side. I have 9 here, and then this 6K to the other side over there. That's 9 equals 2L minus 6K, which is the same thing as 2 times L minus 3K. You see, it's the same trick. This guy is an integer, so that this really says that 9 is an even number, which is obviously true, obviously not true. But 9 is not even. And I like to sort of state something like a contradiction at the end of a proof by contradiction. At the very least, I want to say something around, something in the proof that, you know, I want to signify that I'm using a proof by contradiction. A contradiction. Okay? So ultimately, you see all three of these arguments essentially is based on the same mathematical idea. You basically write down the definition of what it means for an integer to be odd or even, and then you sort of manipulate. That's sort of like the high-level picture, but when it comes to the implementation, the details could be different. Any questions about any of this? Can you speak up?
I mean, I'm still wondering on the last step. Plus 9 is equal to, is that 9?
So here?
Yeah, before the equal sign.
Okay. So do you agree that 2L plus 1 equals 6K plus 10? Okay, so I can send 1 to the other side.
Oh.
10 minus 1 is 9.
I see.
Any other questions? Yes?
Could we also have divided the 6K plus 10 into a 2 times 3K plus 5?
Yeah, there are infinite many variations of these things, yes. Any other questions? Cool. So that's it. These are the 3 methods. There are a couple more. Well, the more important one that we're going to spend some time on is what is called proof by induction. When you have sort of like a statement that is indexed by integers, let's say. For instance, the sum of integers from 1 to n or something like that. There it becomes useful to use this thing called induction. But these are sort of like the methods that's going to be helpful for this week's problem set. Yes?
If after I perform those statements and then I just like n equal to 2k plus 1, then do the same stuff, but when I got this like 3n plus 7 is equal to 6k plus 10, then I factor that 2, like 2 times 3k plus 5, then it's a even number. It's not odd, so there's a contradiction. Can I do that? Is that correct or not?
Well, I mean, insofar as you get a contradiction, it is correct. But, okay, so here's the thing, though. Yeah.
So I'm wondering how can I do that?
So ultimately, do you get a contradiction? Ultimately, do you get a contradiction in that?
Yeah.
Okay, then yes.
Oh, see that.
Yes. Yes.
So if we do something like this on the homework problem,
Yes.
would that be full marks?
Why shouldn't it be?
Great. Just making sure. If we needed-
No, it's good. It's good. Just check everything. Good. Any other questions? Okay. I want to say a couple more words about this, about relations. And I want to discuss functions and stuff like that. One thing I wanted to do last time that I forgot is a bunch of operations that you can do with relations. Let's discuss those first, and then we're going to finalize with this notion of a function. Operations with relations. Now these are described in the textbook specifically for functions, and in a second we're going to see how functions are really nothing but special types of special types of relations. But all of these can be defined more generally for relations. What I'm not going to do is I'm not going to give examples. It's going to be your job, okay? And this is going to be a standing exercise. Whereas in a sort of calculation-based math class, let's say, what is important is in class is to have a bunch of examples and stuff like that. Here it's going to be a little different. Building examples is going to be part of your job, like I discussed on Wednesday. That's one of the methods in which you approach problems. Okay, so I want to have 3 sets. And I'm going to have let's start like this. One relation R from X to Y, and then yet another relation, let's call it S, from Y to Z. Recall the notation here. X times Y was the Cartesian product. It's the set of all those ordered pairs, x comma y, lowercase x comma lowercase y, such that lowercase x comes from uppercase x and lowercase y comes from uppercase y. And then this was the set of all subsets. It was a power set. I'm just saying this R is a subset of x times y, and likewise for S. And let me also take a subset of x, A, and P of x. Okay, now I'm going to define a bunch of things. Yes?
Shouldn't the subset symbol be used instead of the element symbol?
No. Okay, good point. I could have equivalently written this like this. When you put the P here, you go to the meta. Okay, so it allows you to sort of replace this expression with this expression. It's the same thing. And in fact, in problem set 1, you're going to see something like this. Okay. Part of it is because I want you to think step by step and sort of unpack the definition and sort of repack them and all that stuff. Okay. So I need the following things: domain, image, inversion, composition, restriction, and image of a subset. So domain, these are definitions. Oh, this is a certain subset of X. And I'm going to write it like so. Dom of R is the set of all those X's in X such that R relates X to some Y. Okay. Image or range of R is sort of like the opposite thing. Set of all those y's such that for some x, x is related to y. I understand that it's a barrage of notation and definitions and stuff like that. Hopefully throughout the semester, these are going to be more and more easier to parse. These are not super important for us. That's why I'm sort of fast forwarding it. I think I am legally obliged to mention something about these. So inversion, or so let's say inverse of R. Well, it is denoted by R to the minus 1. And this is the following. It's a set of all those y comma x's such that x comma y is in R. This is sort of like a transpose, if you want, if you're familiar with matrices and stuff. Next up, composition. And so this is where I start using this other one. And so S composed with R, the notation for this is this circle, small circle. Well, it's the set of all those pairs, x comma z, in x times z, such that for some y, x is related to y via R, and y is related to z via S. Okay, and then restriction and image. So now I want to use this subset A. The restriction of R to A, I'm going to denote by R and then a bar, long bar, and then I'm going to put A. It's almost like R evaluated at A in terms of like integrals and stuff. And so this is nothing but x comma y in R such that I'm restricting the input value to be coming from A. And then finally, the image of A under R is the following. This is denoted by R of A. It's almost like a function. And in fact, part of your, so it's going to be a part of problem set 1 to really make sense of this expression as a function. Well, this is nothing but the set of all those y's such that there's an A in A such that A comma y is in R. This really is the same thing as the image of the restriction. So you can write it like this as well. Exercise is to come up with visual representations, visual examples for all of these. And I would suggest just take x, y, and z to be, let's say, the unit interval. This is a standing exercise, actually. Even when I'm not stating this, it's always, you should always take it as an exercise to come up with examples. Questions? I realize this is too much, too many definitions without justification and stuff. Let's just say that we're gonna use these things sporadically speaking, let's say. It's just a bunch of terminology and notation. And in the future, if we end up needing to use things, we're gonna I'm gonna remind you these things. Okay, we have a couple minutes. Let me just finish this relation, this definition of a function. So this was related to the third way of defining or constructing a new set out of old ones. Recall that what we said was that for R, a relation, it is the graph of a function if the following holds. Graph of a function if for any 2 points in R, if x1 equals x2, then y1 has to be equal to y2. In this case, I'm going to put A to be equal to the domain of R as I just defined. I think I'm running out of time actually again. This is cursed. I still couldn't finish this definition. We're going to continue this on Monday. Thank you. Have a nice weekend. I'll see you on Monday.